In this video, we are going to learn on how to determine member end moment considering support settlement. So this is a continuous beam A, B, C, D, okay, subjected to UDL along member CD. Okay, in addition to the load shown, support B is settled by 20 mm. Calculate the member and moment using moment distribution method. Okay, now we are going to analyze this beam. So remember FEM is actually can occur due to loading as well as delta. So we have two types of FEM in this question. Whenever settlement is given, information about settlement means delta is given in the question, means that we have to consider that. Okay, so anyway, for the stiffness factor and distribution factor, it is the same. So we just need to consider the combination of loading and support settlement. Okay, in step number 3. Okay, we will start with step number 1 first, as usual. Okay, for step number 1, we have to calculate stiffness factor first. Stiffness factor in order to calculate distribution factor. So for the stiffness factor, so we assume that all EI for each member is constant. So and NA and ND are fixed N, so we have to use 4 EI over L. 4 EI over L for all members. AB, for AB we use 4 because NA is far and fixed. BC internal we use 4 EI over L. CD, D is far and fixed, so we use 4 EI over L. Okay. And for distribution factor, we use K divided by total K. Member stiffness divided by joint stiffness. Member stiffness divided by joint stiffness. Stiffness factor, this is step number 1. Step number 1. Stiffness factor N. Distribution factor. This is DF. Okay. So we list all the members. It is actually referring to N member. Member N. So there are 3 members. One member has 2 N. So in total, we have to determine 6 member N moment. So for the column, for the table, we should have 6 column. For AB, for BA, BC, CB, CD, and DC, 6. Okay. The K. Okay, in terms of EI, for AB, we will use 4 divided by 3. This is 4 divided by 3. It is the same, 4 divided by 3. Because it is the same member. Okay, for BC also, K, it is 4 divided by 3. For 4 EI over L, L is 3 meter. Okay, and for CD, it is 4 divided by 5. This is 4 divided by 5, 4 divided by 5. Okay, this is the same member, this is the same member, this is the same member. Okay, and after that, we will continue to calculate distribution factor. NA is fixed and it is 0, and D is fixed and it is 0. Okay, BA and BC, so we will get here is 0.5, 0.5. Okay, and for CBCD, it is 4/3 divided by 4/3 and 4/5. Okay, so the answer is it is 4/3. We have to divide by 0.62, 0.625. So this is 0.625. Okay, 0.625. So for the other one, we just minus by 1. So we get 0.375. 0.375. It is 375. Because total this must be 1. Distribution factor at joint C is 1. Distribution factor at joint B is 1. Okay, this is distribution factor. Okay, now we want to move to the next step, step 2 here. Okay, we want to calculate fixed end moment. Fixed end moment. Fixed end moment. Okay, so we have 2A here. 2A, we want to calculate fixed end moment due to loading. And due to loading, when we look at the diagram, there is no fixed end moment for AB, no fixed end moment for BC. So we should determine fixed end moment for CD. And by assuming both end fixed, we will determine FEM CD and FEM DC. Okay. And remember, when we calculate fixed end moment, we just need to assume that both end fixed. Both end fixed. So due to loading, we have member, this is member C and D. It is UDL, 5 meter. And the loading is 10 kilonewton per meter. Okay, it actually produce this fixed end moment in this direction. The moment is opposite sign. The moment is opposite sign for C and D because it is behavior. The moment we push back the beam to its original position. So that's why it behaves like this. Okay, so the formula is WL squared over 12. It is WL squared over 12. So WL squared over 12, it is W is 10, L is 5 squared over 12. WL squared over 12, it is equivalent to 20.83. It is 20.83. The fixed end moment. This is due to loading. And we have actually 2B, step 2B. Okay, due to support settlement. At B. Okay, so for support settlement, so look at the beam after settlement. It is like this. Okay, let's say this is A, B, C, and D. And support B is settled means B move to new position here. This is B prime. Okay, and the delta is 20 mm. A remain at same position, C remain at same position. Okay, so when settlement occur, the most important thing is we have to determine where is the delta, and we just need to draw the triangular. Okay, means that we have to join A and B prime. Okay, this is one, the first triangular, and the other one is from B prime to C prime. Not C prime, C. Okay, A to B prime, because A, B prime is new position after settlement, and B prime C is also new position after settlement. CD remain at same position. Okay, so the red color here representing the behavior after settlement occur, and this is actually delta, and the delta is 20 mm. And due to support settlement, due to delta or FEM, so this is the new position. This is the new position. And remember, the moment, the fixed end moment will push back the beam to its original position. Original is this. This is original. Original is horizontal. This is new. Original is horizontal. This is new position. So moment, fixed end moment will push the beam go back to its original position. So we have to push this and this. We have to push the two end so that the beam will move back to its original position, which is straight position. So we have to apply in this direction. Okay, in these two direction. It is the same direction so that the beam will go back to straight position, straight and horizontal position. Okay, so this is actually the fixed end moment. This is fixed end moment. This is also fixed end moment. Direction. Okay, so that is for AB prime. That is for AB prime. So what we can conclude here is, okay, normally for settlement for delta, it will produce the triangular. Okay, it will produce the triangular. This is the delta. Okay, this is A, B, and B prime. Okay. Okay, and this is 90 degree, the triangular. And if this is original, and this is new, okay, look at the angle here. This one is called as chord rotation. This is chord rotation. Chord rotation means the behavior from original to new position. The chord rotation, the angle. So the angle between original to new position, it rotates clockwise. Rotate clockwise. So when the angle is rotate clockwise, when chord rotation rotate clockwise, FEM. Okay, FEM. Chord rotation rotate clockwise. FEM is counterclockwise. It is opposite. Between angle, the chord rotation, and the FEM. It is opposite condition. When angle is positive, FEM is negative. Again, when angle is positive, FEM is negative. So the formula is very simple. FEM, okay, it is member AB. And this is equal to FEM BA. And this is actually, okay, producing negative FEM. Negative FEM. Here is negative FEM. So we put negative. Okay, and the formula is 6 EIA I delta over L squared. So this is the formula. This is the formula. So FEM AB, FEM AB, FEM BA is negative 6. Let's say E is 200, I is 500, delta is 0.02. It is 20 mm divided by length. Length is 3 meter. It is 3 squared. So we will get this is equivalent to 6 times 200 times 500 times 0.02 divided by 9. So we get 1333. 1333.33. It is negative. Okay, so this is kilonewton meter. So this is at fixed end moment for AB, and it is negative because the behavior is like that. Okay, it is counterclockwise. Counterclockwise. So same thing we have to do for member BC. Member BC after side sway. After settlement. After settlement. Okay, if this is for AB, so now we move to BC. This is for AB. This is for AB. Now we move to BC. BC. The triangular occur after settlement is like this. Okay, so this is B, this is C, this is B prime. Okay, the original is horizontal. This is new. Okay, always remember that we measure the angle or the chord rotation from original. This means that the chord rotation is counterclockwise. The angle, the chord rotation is counterclockwise. So FEM is clockwise because it is opposite like this. When this beam, this is the beam after side sway, after side sway is for frame. This is settlement, after settlement. And this is the incline. So incline is new position. It has to move back to horizontal. So we have to apply moment like this. So we push back to this incline to horizontal. That's why we get this. That's why we get this direction. It is positive. It is clockwise FEM, means FEM is positive. Clockwise FEM means FEM is positive. Okay, so for member BC, FEM for member BC, it is equal to FEM CB. Both have same sign. And okay, the behavior of FEM, it is clockwise, so it is positive here. Okay, the formula is 6 EI delta B, delta B is 20, delta B. Okay, divide by L. This L is also 3 meter, so we will get the same, but it is positive. Okay, it is positive, 1333.33 kilonewton. Okay, so what should we do after this? What should we do after this? Okay, we have to plus these two. We have to plus this. This is actually FEM CD. FEM. This is FEM CD, which is negative 20.83 kilonewton meter. And we have FEM DC is equal to positive 20.83 kilonewton meter. So before we move to the table, the value we have to total. Okay, so we summarize all the fixed end moment here. Okay, fixed end moment, the total fixed end moment due to loading and due to support settlement. So FEM or AB. FEM AB is negative 133.33 kilonewton meter. FEM BA is also negative 133.33 kilonewton meter. FEM BC is positive 133.33 kilonewton meter. FEM CB is positive 133, okay, 1333.33 kilonewton meter. FEM CD is negative 20.83 kilonewton meter, and FEM CDDC is positive 20.83 kilonewton meter. Okay, so this is total moment, total FEM, and we will use this in the table to calculate member end moment considering support settlement. Considering support settlement, and of course when support settlement occur, the loading is there, so we have to combine these two. We have to combine these two FEM, and we continue the distribution process in the table as usual. Okay, so I want you to continue for 1 hour session today. Okay, to continue the table, just the table, and see the result after that. Okay, and then after that, I want you to from the table, the moment that you get, please continue to try to draw the bending moment diagram and see what happened. Okay, after the okay, the settlement occur. Okay, so this is the use distribution factor and use this fixed end moment in the table and find the fixed end moment, and after that draw the bending moment diagram. Okay, so that's all. I want you to continue this for 1 hour session class today to finish this example, this question. Thank you very much.